In this video, I'd like to talk about Hooke's law. Hooke's law has to deal with forces due to a spring. So if you look at this first diagram here on the top left, we have a spring, and this spring is at a position which we call equilibrium. At this point, the spring is neither stretched out or compressed. It's quite happy to stay in that state. So let's just write that down. So here we have the equilibrium position. And we usually put the equilibrium position on a coordinate system at position 0. So in this case, if you look down near the bottom of the screen over here, we have the positive x direction going to the right. So in this first diagram, the displacement is 0. This is the displacement of the spring is 0. And there's no force due to the spring. So there's no force by the spring. So now let's go to the second diagram. In the second diagram, we've pulled back the spring by a distance of x. And once we've done that, the spring is exerting a force back towards the equilibrium distance, the equilibrium position. So we apply a force F to stretch the spring a distance x. Okay. And now let's look at this third diagram. If we double the amount of force, what happens is that we double the distance we can stretch the spring. And one thing to note in this previous one, when we apply this force F, this is the force but the hand is exerting, and that's equal in magnitude to the force that the spring is exerting, but in the opposite direction. And for this third diagram, we have to apply a 2F force to the right, while the spring is exerting a 2F force to the left. And that force is the result of us pulling back the spring a distance of 2x. So for a displacement of 2x, we have to apply a force of 2F. So this x is in relation to the previous diagram, this x here. So these two x's are the same, it's just 2x is twice the amount. So we can summarize all of this into a nice equation. First of all, you can notice that if the amount of force is proportional to the displacement. So let's just write that down. We have force is, and this is the spring force, is proportional to the displacement of the spring. And in fact, there's a constant of proportionality. So the magnitude of the spring force is actually equal to a constant k times the displacement. And here, k is just a constant, and it has units of newtons over meters. And whatever the constant is, it depends on the spring, what it's made out of, and various other things. So we have the spring force is equal to a constant times how much the spring is displaced from its equilibrium position. And in fact, we can make this, we can write this in component form. The spring force is always kind of in, well, we can think of it in one direction. So for this case, what we have is in the x direction, the force due to the spring in the x direction we can write as minus k times delta x. And this right here is called Hooke's law. Now, where does the minus sign come from? Well, that minus sign is the result of, we can either compress or stretch this spring, and the spring by the force due to the spring is always in the opposite direction to the displacement. So that is why we tack on that negative sign here. Remember, up here we were looking at the magnitude of the force. Down here, this is the force due to the spring with the direction. And remember that delta x is the displacement from the origin, or from the from equilibrium. Okay, so Hooke's law. Why don't we consider an example? I have an example here of a 9.09 kilogram mass placed on top of a vertical spring. So let's draw what this might look like. Let's get a straight line here. So let's consider this line here to be the ground. And we have a spring. Here's my fancy spring. And it's a vertical spring. And right here, the spring is neither compressed or stretched. It's in its equilibrium position. So we can draw a line across to indicate the equilibrium position. Okay, so that dotted line, dashed line there represents the equilibrium position. And what we do is we put a mass on top of this, and this has a habit of compressing the spring. So here's our mass m, and there is this vertical displacement right here of 4.18 centimeters. So we have 4.18 centimeters. And we're interested in the force constant of this spring. So the way I'm going to solve this problem is I'm actually going to draw a free body diagram for this mass. So here is my coordinate system. I'm only going to care about the x direction, the y direction, the vertical direction. All my forces acting on this mass are either up or down. So here's our mass, and we want to draw the forces. So first of all, there's a weight which is downwards due to gravity, and there's a spring force upwards. That's the restoring force of the spring. We're compressing the spring, and it wants to be pushing back to get to its original position. And this mass is in equilibrium. It's quite happy to be there. These two forces are nicely balanced out. So we'll call this Fs for the spring force, and we have the weight. And our net force is equal to 0. Alright, so we have our free body diagram. Let's turn to Newton's second law. So in component form, we have the sum of the y components, and that's just going to be the y component of our spring force, which is the spring force is in the y direction, so that's just the magnitude of the spring force minus the magnitude of the weight, and that's equal to mass times acceleration. But our net force is 0, so our acceleration is 0, and this equation is equal to 0. So we can solve for the spring force. The spring force is equal to the weight, which is just the mass times the acceleration due to gravity. And we want to find this force constant of the spring. That's the, if we go back, that's this K in Hooke's law. So we know the force due to the spring is equal to minus K times the displacement. So that's delta y. And so I can solve for K. K is just equal to minus mg over delta y. So our mass is 9.09 kilograms. I forgot the negative in front. We have the acceleration due to gravity. And we divide by our displacement. So our displacement is actually downwards, so it's negative 0.0418 meters. Great. And if you notice, we're going to get something positive, and the spring constant in this case, I believe, is 21.33 newtons per meter, and to 3 sig figs you can round that to just 21.3 newton meters. Okay, there's Hooke's law.